For the electrophilic substitution nitration category, you are replacing the H with NO2, and your nucleophile, sorry, not nucleophile, your electrophile, let me saw the R, sorry, is NO2 plus. So some of you might be wondering, how are we going to get NO2 plus out from nitric acid? How is that even possible? So the next step is something you have to remember. The reason why you need concentrated sulfuric acid. So take a while to read this particular segment. Okay, I'll read it out. In a reaction with concentrated nitric acid, concentrated sulfuric acid will function as a Bronsted-Lowry acid. So being a stronger acid, in a way, it donates a proton to concentrated nitric acid, which loses a water molecule to give NO2 plus as the electrophile. Now, in case you're wondering, what in the world is going on, it's actually something like this. I'm not sure whether you remember the structure of NO3. This was the structure of NO3, right? I hope you remember the Lewis structure. There's actually a dative bond. If there's no dative bond, then there's no way this structure will work. Okay, so there's a dative bond. Oops. Now, what happens when it says it donates a proton? What is it? Let's be very clear. It is sulfuric acid, H2SO4. So there's a H plus. Let's say there's H plus from sulfuric acid. This bond, maybe I should draw it this way. Okay, let me adjust a bit. Let's draw it this way. Yes, that's better. Okay, this bond. Why does the screen keep moving? Okay. So troublesome. Okay, wait. Okay, yes, this works. Okay. This double bond, no, not the double bond, what am I talking about? Not this double bond, this NO bond, okay, this NO bond breaks and both electrons go to H. So this whole thing forms H2O. Then you may be wondering, I don't see any H2O here, but there's a H3O plus, which then combines with H plus from another H2SO4. And finally, it forms H3O plus, which is this one. And of course, if you consider what happens to NO, the rest of the molecule, the bond breaks, right? So N is short of an electron, right? So naturally, it becomes the electrophile with a positive charge. So that's what happened to nitric acid. So that's why you need concentrated nitric acid. It's a very concentrated sulfuric acid will be able to act as a Bronsted-Lowry acid. Now, once the electrophile is generated, the rest of it actually, I don't know whether you realize it, is the same as halogenation. Again, you have your benzene ring. Draw an arrow from inside the ring to attack the electrophile. And there's a slow step. You form the carbocation intermediate. Don't forget the arc and the positive charge. Make sure your carbon has 4 bonds. And you're done with this second step. Third step, again, the CH bond breaks. Okay, CH bond breaks. And where does the H go? The way it absorbs the H. the H plus is absorbed by the HSO4 minus, and the catalyst is regenerated. Okay, along with the organic product. And this is your nitration reaction. So I hope you can see the similarities between this and the previous mechanism I showed before for halogenation. But I want you to remember this one, right? You need 55 degrees Celsius, okay, for just benzene. No other substituent groups, it's just benzene on its own is 55 degrees Celsius. Right, so this is the nitration of benzene. Now, if you use excess concentrated nitric acid, okay, and you use a higher temperature, you can actually end up with multiple substitutions. So this is one example. This one is dinitrobenzene. So this 1,3-dinitrobenzene. Now some of you are thinking, why not 1,2? Why not 1,4? Again, there is a reason for that. We'll talk about it later on. So anything for organic chem, for a lot of these substitution reactions, usually we will just ask you to stop at the first substitution. You don't need to keep on giving all the extras. Okay, so look at the context carefully, and usually we only ask for a single substitution. So that's all you need to do. Okay. Now you realize, right, that when you do it this way, the overall reaction, did they show? Yeah, this is the overall reaction. H2O is actually considered a product. Okay? H2O is considered a product here as well. So just be careful. And with that, we are done with our second example of this mechanism for nitration. For our final example of electrophilic substitution mechanism, we'll use Friedel-Crafts alkylation. But by now, you should already see the similarities. Right? First step, have the halogen have something to generate the electrophile. So Friedel-Crafts alkylation is in a way similar to halogenation in that you need a halogen carrier. So again, the similar thing will happen to generate the electrophile. Okay, the Br goes to your AlBr3. Why does it go to AlBr3? Again, the same thing. Empty orbital on aluminum. Right? After that, you have your electrophile react with the benzene ring. So remember, draw an arrow from inside the arc, inside the circle. Okay? Don't need to squeeze in between the lines, no. Okay, just draw from inside the circle. Okay, draw towards the electrophile. Slow step. Make sure you have the arc with a plus sign. Carbon with 4 bonds. And you're done with drawing the carbocation intermediate. After that, CH bond breaks. Arrow goes back in. Okay, arrow goes back in. Okay, good to point it towards the positive charge. Make sure you have your halogen carrier with the extra Br minus on it. Fast reaction. Catalyst is regenerated. You get your organic product and HBr. So this is your mechanism for alkylation. If you want to do for acylation, you realize it's almost also exactly the same. So with this, you are now ready to attempt self-check questions 1 and 2. Please go and try it yourselves.